Hello, Professor. The title of our group research paper is PID-inspired inductive basis for deep reinforcement learning in partially observable control tasks. And next, this is our content. Next. Now I will introduce the background. In real-world control tasks, the agent often cannot observe the full system state, so it must rely on history, making the problem a pure MDP. Next. Traditional history encoders like RNs, LSTMs, and transformers are powerful, but they are too complex for control tasks and easily overfit to simulator dynamics. Next. In contrast, PID controllers have worked reliably for over 100 years using only very simple temporal information. The current error, the accumulate error, and the change in error. Okay, then I will pass it to my friend.
Hello, teacher. I'm going to introduce three parts of my motivations. Next. First is PID inspirations. PID controllers work extremely well with just simple time operations. The robust show us that effective control may not need complicated models. This observation becomes the starting point of the paper's motivations. Next. For the second part, missing inductive bias. Deep RL usually use RNN or transformer, but these models weren't built for control text. They don't include the simple temporal structure that PID naturally uses, creating a gap between classic control and the model RL. Next. For the last part, research aim. The paper scope is to bring PID-like structure into deep RL. By adding a simple and stable inductive bias, the authors aims to improve how RL handles temporal information in control settings. Okay, that's all for my part. Next goes to the challenge.
We talk about the challenge next. The first is the partial observability and the environment mismatch. The consequence is that a policy network must use the history of the observations to infer the current state, and the sim to real gap risk is overfitting. Next. And the architecture gap, we should balance the flexibilities and the robustness. And how to balance these two is the question. Next. And this is about the disadvantage of the current method. The limitation is the misfit. These architectures are designed for the NLP, and the disadvantage is the too flexible and easy overfitting. And when the dramatic parameters are changed, the performance decreases substantially. The next part is the methodology.
Hello, I will talk about the methodology. And this purpose, two PID inspire historical encoder designed for control system. One is PID encoder, and second is generalized PID encoder. And PID encoders extend the classical PID controller concept into a feature encoding method, and it transforms the observation history into three types of signals. The first is a p-term represent the current deviation. Second is I-term represent the cumulative deviation, and last one is the D-term represent the short-term change. Yeah, this is the output of it, and it uses the multiple input and multiple output policy. And then it's GPIDE extend PIDE by allowing the waiting, attention, and richer temporal feature extractions. It has two core concepts. First is the multi-head architecture, and second is end-to-end learning. And its high-level floor is use sequence of observation actions and reward as input and process from feature projections, history aggregations, and finite decoding. The output is used latent representation vector ZT. And the internal process flow is, and the step one is the feature projection is take OAR into a feature space, and then in the step two perform a weight simulation of feature vectors, and last in the decoder is contented the output from all head to form a final encoding ZT.
Hello, sir. I will introduce the experimental procedure. To evaluate the generalization and robustness of the GPIDE model, the author designed two experiments that simulate realistic and challenging control scenarios. An ablation study was also conducted to verify the contribution of PID-related components. Next. First, in the MSDT experiment, the model was tested on mass spring damper and DMSD system with 3 and 8 parameters. Policies were trained under 3 conditions: fixed parameters, slightly changed parameters, and largely changed parameters, and then evaluated under the largest parameter shifts to assess true generalization. Next. Second, in the navigation environment, the agent must reach a 2D target efficiently while being penalized by using large forces. The key challenge is a friction mismatch. Training is done in a frictionless simulator, but testing takes place in an environment with random friction coefficients. This forces the model to infer unseen dynamic purely from past observations. Next. Finally, the ablation study compared 3 variants: ES using only exponential small fin heads, ES plus sum, adding a summation head to represent the integral term, and last one is pure attention, replacing all heads with attention models. That's all for my part.
Thanks, Xinzhe, and I'm going to present the experimental outcomes from this paper, aiming to answer the following 2 questions. And next. First, let's address the first and the most critical question: how do the PID or GPID perform on tracking tests, especially in terms of robustness? The experimental data gives a positive answer, both when semester parameters changed drastically and when transforming from the simulation to reality. GPID demonstrated superior robustness. As you can see in the table left, for the complex DMSD test, in testing with large parameter variation, GPID scored 83.3 on average, vastly outperforming the GRU. Meanwhile, the navigation test on the left shows that when transforming from a no-friction training environment to a friction testing environment, GPID's performance drop was much smaller than GRU's. And next. And then how important each type of head in GPID? The research found that for ES head, the model performed on par or better than the full model. It does the core work of smoothing information. And for ES plus summation head, in the most complex tests, the ES plus sum configuration outperforms the full model. And this shows explicit summation in critical for complex tests. And for the attention head, it shows large negative values across the board, and its performance drops. This proves attention failed completely here, which seriously interferes with the learning. And next. This paper draws on a simple insight gained from classical PID control, providing a more powerful and reliable solution for deep reinforcement learning. And next. That's all. Thanks for listening.